earthquake. Or was it an earthquake? And where did it occur? Answers to both questions will in part be found in these Oregon hills and in similar areas where the Advanced Research Projects Agency, ARPA, has established Seimsic Sentinels through its VELA uniform program for detection and identification of distant underground nuclear weapons tests. Our Earth is in a state of perpetual tremor. Its movements range from imperceptibly slow to inconceivably rapid. They are minute or massive. Since time began, the Earth's shuddering violence has plagued mankind. The yearly toll is figured in hundreds, sometimes thousands of lives, and in millions of dollars. And now, earthquakes provide still another problem which man must solve. This Earth disturbance is man-made. It is the result of an underground nuclear weapons test. But to the delicate seismographs on which intensity and direction of earth shocks are measured, there currently appears to be little difference between a buried nuclear explosion and an earthquake. Since there are thousands of quakes each year, we're faced with a complex problem whose solutions lie in a better understanding of the science of seismology. Under an ARPA program supervised by the Air Force Technical Application Center, AFTAC, Texas Instruments Incorporated constructed and operated 3 seismological observatories in sparsely settled areas of the U.S. Observatories are located at McMinnville, Tennessee, Vernal, Utah, and Baker, Oregon. These research stations provide data for determining differences in the seismic signatures of earthquakes and underground nuclear explosions. In brief, this is how the Seimsic Sentinels function. Observatories have arrays of sensitive seismometers which figuratively feel minute Earth movements. They're buried in geometric patterns which differ from station to station. Individual dots represent single seismometers within the pattern. They detect Earth movements as small as a millionth of an inch, or in the 10 millimicron range. In comparison, a flu virus is 60 millimicrons in diameter. Seen under magnification, the width of a human hair dwarfs the width of the minute Earth movements detected by the seismometers. A seismometer with its protective metal cover removed shows the coils and the mass and demonstrates how the mass moves with Earth motion. When we simulate ground motion by striking the seismometer, the electronic impulse created is very evident on the monitor oscilloscope. Although actual ground movement is much less than the force of the blow, the impulses are generated in the same manner. These minute voltages detected at the seismometers can be amplified as much as 1 million times. Amplified signals are relayed to the central instrument console. Here they are simultaneously recorded in analog form on heat-sensitive paper at a device called a helicorder. On 16mm film at a bank of developers, and on magnetic tape for later playback and further analysis. This schematic drawing of an earthquake seismic record shows background noise and the arrival of a signal. The time of the signal arrival is indicated on the record, and the signal is defined in terms of period and amplitude. Period is the time required to record a complete cycle. Amplitude is the amount of trace deflection. Here the period is about 1 second. On actual record, an amplitude of 10 millimeters indicates ground movement of 60 millimicrons at normal observatory magnification. A wide variety of seismic waves is detected by the seismometers. In general, we can refer to them as compressional waves, shear waves, and surface waves. And there are several different types of each of these. The path which the wave takes from the earthquake to the seismometers at the observatory determines its identification. The P wave, a compressional wave, follows this path, arriving at the observatory in advance of other waves. The PP wave is reflected from the surface and arrives second. The shear waves, S and SS, take the same travel paths as compressional waves, but arrive later due to their slower velocity. The L wave travels along the Earth's surface, arriving last. Comparison of wave arrival times at several stations determines the location of the Earth disturbance. Since seismic signals detected are of such minute amplitude and so complex in nature, the sites chosen for observatories had to be in areas of low seismic background noise. So there could be no industrial plants, railroads, oil pipelines, or similar activities within several miles of the area, for these operations produce seismic vibrations which would interfere with monitoring of the desired earthquake or nuclear explosion signals. Accessibility in all types of weather was a prime requisite of the sites. Telephone and electrical service were also must items. The birth of these stations did not come about easily. Miles of road were either built or repaired to ensure accessibility. And at each location, a strict schedule was kept for the delivery and pouring of concrete for instrument piers and foundations. It was especially important to provide a vibration-free platform for the sensitive amplifiers. At each observatory, these amplifiers are mounted on isolated concrete piers which extend to bedrock. Functional is a one-word description of the prefabricated aluminum buildings which house observatories at Baker, Vernal, and McMinnville. Recording buildings were standardized without frills at each location for optimum ease of construction and lowered cost. Temperatures at individual sites range from 20 below zero to 100 degrees above. Each building is well insulated, heated, and air-conditioned, for operations go on 365 days a year. Concurrent with construction of the central recording buildings, the seismometer array was installed. Each seismometer is encased in a waterproofed, thermally insulated steel vault set into bedrock. Vaults are 4 feet high and 3 1/2 feet in diameter. Seismometers are installed, adjusted, and checked. Vaults are later covered with several feet of earth for further insulation, but can be re-entered if the need arises for maintenance or modification. At each observatory, an average of 35 miles of insulated cable connects the seismometers with the central recording building. The cable is not buried, but the delicate instruments it connects are guarded from possible lightning damage by special protectors which serve as fuses in the array area and at the central recording building. Sensitive ears which can hear a seismic whisper hundreds of miles away would be deafened by a lightning bolt. Seismic signals are transmitted for amplification to the phototube amplifier room. The instrument console handles conversion of the electronic impulses into several formats. Especially important is the recording of the signal on magnetic tape, which can later be played back for analysis and interpretation. Signals are taped uninterrupted 24 hours a day. Should a commercial power failure occur, the instrument console has a built-in emergency power supply which takes over immediately. An extremely accurate timing device is included in the instrument console, since the recording of events in their proper time sequence is a criteria without which the records would be meaningless. Remote calibration of the seismometers can be made at the instrument console and checked instantly on the helicorder. VELA process the data and provide optical magnification so that each event can be closely studied. Its amplitude and period is incorporated into a daily report which goes to the United States Coast and Geodetic Survey. The three stations record an average of 20 distant Earth disturbances each day. As a result of these reports, along with reports from similar stations throughout the world, the observatories each week receive information back from the Coast and Geodetic Survey regarding all earthquake locations. Individual stations recheck their own data on a view screen and are able to closely analyze all phases of the events and relate them to known Earth disturbances which have been pinpointed in Coast and Geodetic Survey reports. Many valid seismic signals are either too weak or too effectively masked by background noise to be detected by conventional state-of-the-art instrumentation. Under a separate contract to AFTAC, TI made an exhaustive study of seismic signal and noise characteristics and evolved a new concept in data processing and presentation. In addition to its normal operation, the observatory at McMinnville was used as a laboratory to operationally test this new multiple array processor, or MAP. It is designed to accept and process real-time data from all seismometers in the array simultaneously, to discriminate against seismic background noise and present the valid information in a manner so that interpretations can be made of events not easily observable with conventional equipment. 10 separate displays of data can be made with MAP. One of these experimental displays is made on an azimuthal indicator whose readout resembles a television screen. An outline of the hemisphere is superimposed on the screen. Signals and random noise are both recorded. Only direction and intensity of the event is shown. The pulse indicates the direction from which the strongest signal is coming. It may be a nearby quarry blast or a distant earthquake. All instruments at the observatory operate 24 hours a day. This visual array monitor is also a part of the experimental multiple array processor. Each light represents a seismometer. The brilliance of the light is proportional to the strength of the signal being received. Each of the observatories was completed on schedule. The Blue Mountains Observatory near Baker, Oregon was dedicated on September 22, 1962. The Uinta Basin Observatory at Vernal, Utah, and the Cumberland Plateau Observatory at McMinnville, Tennessee, were opened on December 19, 1962 and February 16, 1963, respectively. Citizens of the areas in which the observatories were built, contractors, representatives of the Defense and State Departments, local and national political figures, all took part in the dedication ceremonies. All are aware that these stations have a vital task to perform. So, was it an earthquake or a buried nuclear test? Your seismic sentinels are helping to provide an answer.